Precalculus, Unit 2A, Day 7 notes. Okay, we're just going to do 3 word problems today, and then we'll end up following that up with a volume optimization project in class, which would be kind of fun. Okay, but let's look at it. Let's just look at example 1. Okay, it says, suppose you have 210 meters of fencing to make 2 side-by-side rectangular enclosures. Okay, so let's draw that. So we got 2 rectangles that are side by side, and it says they share a side. Okay, so they share this side right here. What is the maximum area that you can enclose? So this is kind of like saying I have this much fence, and maybe you want to like plant a garden, and you want to get the most square footage, or in this case square meterage, that you can make use of with that fencing. Okay, so you have the fencing, you want to maximize how much area you can put inside of it. Well, we can do this. Okay, we can do this. So there's 210 meters total. Okay, so the perimeter is 210 meters. We know this. All right, how do you find the perimeter of this object? Well, perimeter, you just add up all the sides, the outside. So if you're going to use fencing for all of these, we're going to look at, let's say that this whole side right here is a length. So we got another length up here. And then the little vertical pieces, those are widths. Okay, so we got a W here, and a W here, and a W here. So we got 2 L's and we got 3 W's. Okay, so I can rewrite this as perimeter equals 2 lengths plus 3 widths. Okay, well, since we know that the perimeter is 210, we can rewrite this as 2L plus 3W. Instead of equals P, we can substitute equals 210 meters. Okay, I'll leave the meters out for now. All right, so what can we do to maximize our area? Well, that means we need the area formula, and you should know the formula for the area of a rectangle. Okay, the area of a rectangle has the formula length times width. Okay, length times width for the area of a rectangle. Well, I would love to, and this is, by the way, length times width. That'll cover this entire area. Okay, I would love to put this in my graphing calculator. However, the calculator will only let me graph one variable. So it's going to be y equals something with an x at most. Okay, if I put in more than one variable, it's not going to graph it for me. So I need to solve either for L or W. And once I've solved, then I can substitute it in for either this L or this W, and I'll be able to put it in my calculator. So let's solve for L. Okay, so I want to isolate this L right here. So the first thing I'm going to do is I'm going to subtract 3W from both sides of the equal sign. So that gives me 2L equals 210 minus 3W. If you write negative 3W plus 210, I understand, not a problem, right? And then we will simply divide everything by 2, divide by 2, divide by 2. Every separate term we divide by 2. So length is 210 divided by 2 is 105 minus 3/2 width. So I can take this and I can substitute it in for this L right here in area equals length times width. That will give me my area function in terms of one variable, and this would be my variable W for width. So let's do that. So area equals, instead of L, we're going to write 105 minus 3/2 W. If you're into decimals and you want to write 1.5 W instead of 3/2 W, I understand that too. Okay, that's the L, okay, times the width. So this is length times width. Area equals length times width. So we did some good old-fashioned algebra 2 substitution. Well, we want to maximize the area. Our graphing calculator can do that. So I'm simply going to type this into Y1. I'm going to type it either just like that, or if we want to be a little nicer to our I don't know, our predisposition for wanting to not have the factored form or the parentheses, we can rewrite this as A equals 105 W minus 3/2 W squared, okay? So negative 3/2 W squared. So negative 3/2 is the leading coefficient. It's a second degree polynomial. It means it's going to be an upside down parabola. So what we need to do now, as I just said, we need to graph this and find the max, the maximum value of your area, okay, your Y coordinate. Because it's going to look like this. You're going to want the highest Y coordinate, or in this case, my highest A coordinate, my A of W. So let's go ahead and put that into, I'll put it into Desmos, so it's a little nicer to see on this. All right, so here we have our equation, f of x, or in our case, a of x, equals 105x minus 3/2 x squared. All right, so that's what I've typed into my calculator. And now, don't be alarmed if when you look at this, you say, wow, I don't see the max. Okay, I don't see the max. I just see maybe this part, right in here. You've got to adjust your window. You got to go up higher. You have to see the maximum. So you have to increase your Y max. So let's increase it to 600. No, it's still going up. I want to see the max. I want to see that it's going up and then it's going down. I want to see the increase followed by the decrease. So let's keep going up to 1,000. It's still going up, which just means that our maximum area will be more than 1,000 square meters. That's good. We want as many square meters as we can get. Oh, so if I increase my X max, okay, if I increase it right about to 70, which is what I'm looking at over here to the right, okay, then I can see the bottom part of the parabola. Okay, I can see both halves of it. Now I want to continue going up, 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 up. So I'm going to increase my Y max some more until I finally see it. There it is. Okay. Now, with your graphing calculator, you'll go second trace for calculate. You're going to go left bound, right bound, enter, enter. Okay. And you're hopefully going to get this max, which is at 35, 1837.5. Okay, so let's write those down. All right, so the maximum, we saw that point, max point was 35, 1837.5. Well, that was my maximum f of x. So my x, or in this case my w, my width, was 35. My maximum area, or my a of w, was 1,837.5 meters squared, right? So the question was, what is the maximum area that you can enclose? Well, the answer is 1,837.5, and it's area, so it's always squared. So meters times meters is meters squared, right? That's your maximum area. So the width would be 35 meters. And then your length, well, if you remember correctly, the length back here was 105 minus 3/2 times W. So if you want to find what the length would be, then you substitute 35 for the W, okay, and you can find your length. Right? So if you physically wanted to go out and cut off the fence into the sections, it'll be 35, 35, 35, and then you'll have your pairs of your lengths. Okay, all right, that's question 1. Now question 2. This one is almost identical to the optimization question that you're going to get when you have your piece of paper and you're going to need to create an open box, right? So that's what's going to happen here too. A manufacturer cuts squares out of the corners of an 8x14 piece of sheet metal, like your piece of paper that you're going to be cutting, and then folds the metal to make an open top box, right? So they start with a rectangular piece of metal, and then they cut squares, okay? And they cut them out. And then what they do is they take these flaps and they fold them up. They fold this flap up. They fold. Okay. See if I can, there we go. All right. And they fold this up and they fold this up. Okay. So that when it's folded up, this side and this side are touching each other and it makes a corner, and this side and this side are touching each other and that makes a corner, and then this side and this side are touching each other. Okay, so they're folding it up so that you have a box without a top on it. Okay, but you start off with the big rectangle. Okay, so it says the manufacturer wants to maximize the volume of that sheet metal piece. Okay, so it's going to be an open top box that they're making, just like you're going to make. And they want to put as much stuff in there as you can. So I don't know, maybe it's a toy box and they just want to be able to advertise that they can put in this many square centimeters or cubic centimeters, excuse me, it's volume, cubic centimeters worth of toys. You know, maybe they're putting food in there and they want to get as much food in that box as they can. Right? Who knows what they're going to do with it, right? In this case, it just says, write a function for the volume of the open top box. It says, what is the domain? That's going to be very important. And then find the approximate value of x. Okay. Now, it says that each of these squares are cut out, and the squares are all congruent to each other. Okay, each of these sides is x. Each of these little sides of your square measure x centimeters long. Okay, okay. Now we're going to make our volume formula. So they already gave you that the volume of a rectangular prism or a rectangular box can be found by the formula volume equals length times width times height. So you just need to come up with something for each of those variables so that you have one variable. Well, the height should be the easy one, because when they fold these flaps up, the flaps are going to be the height of x. Okay, so you cut the x centimeter square out and you fold it up, then one side of that square is going to be your height. So your height is going to be x. Now it says here that the paper is 8x14. So this whole side, let's put this neutral color here. This whole side is 8 centimeters. This whole side is 14 centimeters. Okay, so when they make the box, after they fold the flaps up, the box is going to have a base that's this part right here. Okay? This part's going to be the base of your box. And then they're going to fold these X by X squares up. So what is the length and width of the box itself? Okay, well, the length of the entire sheet of metal was 14. But check this out. That 14 had not just one X cut out of it, it had two X's cut out. So the length of the box, we're going to call 14, take away 2X. Okay? Like this side right here. Okay? It used to be 14. They chopped off this X, they chopped off this X. That's 14 minus 2X. So that's the length of your rectangular box. And then you've got the width. It used to be 8 for the uncut sheet metal. Then they cut again, they cut an X out here, and then they cut an X out here. So it's going to be 8 minus 2X. Right? Now, if you wanted to expand that out and put it in standard form, I'm not going to stop you, but I would say this. Putting this into your calculator is going to be just fine. Okay? So, knowing some things about graphs based on factored forms, okay, if you have volume equals, right? I know where my 3 zeros are going to be, my 3 x-intercepts. I know there's going to be 1 x-intercept at 0. I'm going to have 1 at 0. If I have 8 minus 2x equals 0, I know that there's going to be a 0 at 4. And 14 minus 2x equals 0, I know there's going to be a 0 at 7. Okay, so I know that my graph is, it's going to be an x to the first, x to the second. It's going to be a cubic. Okay, it's going to be a cubic, and it's going to look something like this. You're going to have an x-intercept at 0, at 4, and at 7. It's going to be coming. It's going to be coming up. Try it again. Coming up, down, and up. That's what my cubic is going to look like. It's going to have 2 turning points. It's going to be a down, up. All right. That's what it's going to look like. So where is the maximum volume going to be? Well, it's going to be the maximum right here. Okay? It's going to be the maximum right there. Now, why is it? Why isn't it over here somewhere? Well, because of the domain. This is a word problem. We have to think in real life, what would this domain be? Well, take the shortest side. Okay? The shortest side is 8 units long. Okay? 8 units long, and you cut out 2 of those x's. Okay? That's the shorter side. You know that 8 minus 2x in real life can't be negative. It's got to be greater than. I mean, if you want to put equal to 0, I don't know how you're going to get a box with 0 for a width. So I'm going to leave it as greater than. So 8 minus 2x has got to be greater than 0. All right, let's solve this. This is trying to figure out what our domain is going to be for this volume function. The smallest side has got to be bigger than 0. That's what we just wrote. So now let's solve for x. Let's subtract 8. So we've got negative 2x is greater than negative 8. Now we have to divide by negative 2. And because we're dividing by a negative, yes, we change the sign of the negative 8 to a positive 4, and we change the direction of the greater than symbol to be less than. So I know that my x has got to be less than 4 units. Okay, so if I'm looking at my graph here, okay, the 4 is this one right here, that 0. Okay. I know that my x has got to be bigger than 0, right? Because you can't cut 0 or less than 0 from your box, right? So that means that this is the only part that real life is going to allow me to create a box with. Okay, so I need that max. I need the max for this domain. Okay? So since it says, what is the domain? This is your domain. Okay, X, for X, it's got to be between 0 and 4. That's interval notation right there. This here is standard notation. Okay? So since it didn't say you had to do interval notation this time, either one will be fine. If it does say it, make sure you do it. Okay, so from 0 to 4, that means we got to graph this. Okay, so take your graphing calculator. You're going to input this right here into Y1, and you're going to get your window between 0 and 4 for your X. And make sure that between 0 and 4, you can see the max. Make sure you can see the top of that hump. Okay, go ahead and do that. Okay, so here you can see over here in my my function table, my input is 14 minus 2x times 8 minus 2x times x. My graph, I've got my x min here at 0, my x max at 4, so I can see from 0 to 4. But I need to increase my y max, if I have a calculator, above 25, above 30, above 35, above 40. You got to keep going until you can see the top of this little mountain right here. Okay, and it goes right up to here. Boom. So again, if you have your calculator, second trace or calculate, you want max. You're going to go left bound, right bound, enter, enter, and you should get 1.639, comma 82.981 for your max. Okay, so here is our max, our maximum point, 1.639 for my x coordinate. Now remember what my variable was here. It was that x. So that is the length of one side of the squares that you cut out. Okay, so x is going to equal 1.639 centimeters. And then what was the 82.981? Well, that was the V of x. That's the volume. So the maximum volume is 82.981. Okay, so centimeters, length times width times height. Centimeters times centimeters times centimeters is centimeters cubed. Right? And you're going to do that with your piece of paper. You're going to maximize the volume of an open top box that's made out of your, not sheet metal, but paper sheet. Okay? All right, let's finish up with question number 3. So example 3 says, a microwave manufacturing firm has determined that their profit function is P of x equals this lovely cubic function, where x is the number of microwaves sold annually. All right, so we're going to approximate all of the zeros of the function by looking at decimals. So when we plug a cubic into a grapher, like a graphing calculator or even in Desmos, you know, I'm looking at this minus 355 and the fact that this is 0.0014. Okay, these might be some big numbers. So I would like to know what the shape of my graph is. We should know some things about the shape of this graph. Okay, this is a third degree polynomial, or at least it's a third degree function. Okay, so it's an odd degree with a negative leading coefficient. So that tells me I know that it's going to be an up-down that tells me it's going to be an up-down if I'm going to graph. Okay. It also tells me that there are 3 complex zeros by the fundamental theorem of algebra. And I know that there are at most 2 turning points. Okay. So it could look like 1, 2 turning points and down. It could look something like that. All right, so have an idea of what it looks like. And let's go to Desmos and see if we can graph this. Okay, so I have this typed in. My window apparently is not big enough because you can't see it. So you're going to have to increase everything. You're going to have to increase your Y max and your X max. All right. Oh, there they are. Okay, so remember what we said the basic shape of our graph had to be like. Okay, it's an up-down. So if I'm going bigger and bigger, let's say that we want to go lower on the Y max. So let's go further in the negative direction, see what we can find down here. Okay, going down past 300. Okay, there's a little bit of info right here. So there's a turning point way down here at negative 384-ish, right? So looking at this lovely graph, we see that it started up, it went down to 384. Okay. Now there's going to be one more turning point apparently, because this has definitely got the one local min, one local max, and then the up, down, end behavior. So if we're going to get higher and higher, take a look way up here. Again, we just want to see the shape of this graph. So we're going up above 200. We're still going. Okay. So you would play with your window, get your Y max higher and higher. All right. You see, it goes way up there. It goes way up there here. Let's go up into the thousands, shall we? All right, so I just adjusted my window a little bit, zoomed out a little bit, and we can see part of this this cubic. Oh, and there it is. So if we go up to somewhere between 2,400, 2,600, we will see that local max. Okay, so that tells me that, there we go. So my window, I'm going to go, probably from negative 100 to positive 300 for my X min, X max, so that I can see all 3 of the zeros. And if I want to see the behavior of the maxes and the mins, I will go down to negative 500 and up to, well, I got to go well over 2,500. So let's go up to 3,000. So if we go up to 3,000, it's just about like that. All right. So now let's answer our 2 questions. Okay. A, approximate the real zeros of the function. Well, you can see there are 3 real zeros here. So you knew there were going to be 3 complex zeros. They all happen to be real. Awesome. So you would go second, calculate 0, left bound, right bound, enter, enter. Okay, and hopefully you would be able to find this guy right here, which is negative 41.008. But we're really not, I'm not too worried about the negative 41, because remember what X stood for. X represented the number of microwaves sold annually. And you can't sell negative 41 microwaves. All right, so even though we can see it in the graph, in real life, that's not going to be one of our real zeros, okay? All right, now 27.097, right? That's definitely one. And then if you go left bound, right bound, enter, enter, you should get 228.197 for this other real zero. Okay, so those are both positive numbers that could help you tell how many microwaves need to be sold annually to give a profit. So remember, if this is profit, then wherever the x-intercepts are, that means your y, or your profit, is 0. Right? So at those 2 points, you have 0 profit. All right, so approximating the real zeros. Okay, so we saw that it went pretty far down, and it came pretty far up, and ended up back going down again, right? So, yeah, this one here was the 27.097. Okay? So my real zeros, 27.097, and we also had 228.197. Okay, so that was the second one, big guy. All right, so now B, take what we just found in the graph, and let's answer this question. What is the range of microwaves sold that will produce a profit? Now, when they say range of microwaves, it's not like domain versus range, X versus Y. Range of microwaves just means, you know, the lowest amount of microwaves to the highest amount of microwaves that will produce a profit. Okay, so as I just mentioned a little bit before, at these 2 zeros, the profit is 0. If we are down below the x-axis, that's a negative profit. That's a loss. You don't want to be there. For a profit, a positive profit, that would be any point that is above the x-axis. So those points above the x-axis, okay, and again, I understand these are above the x-axis. However, that would be negative microwaves sold, which is impossible. So we're going to go real world application from this 0 to this 0. In between it, everything is a profit. Okay, everything is a profit for the company. Now, there is a max in there. They didn't ask us what that max is. Okay? If they wanted to ask us, then we could have found it. But they didn't ask us. They just said, what is the range of microwaves that we could sell so we're actually going to make money, get a profit, right? So between 27.097 and 228.197, there is profit. Okay, profit exists, right? So again, everything between these 2 x-intercepts, between these 2 zeros, will give us a profit. So we could just use those two zeros as the beginning and end of that range of microwaves. So, I mean, we could express the range where we have a profit with the interval notation 27.097 to 228.197 with parentheses, simply because at those points, there is no profit. Okay, profit is 0. So we cannot include those points. So if you're just looking at the graph and you're thinking about mathematically, it's a nice answer. Okay, that's a good range of values, but this is a word problem. We're talking about the number of microwaves that can be created, manufactured, assembled. Okay? In this particular interval, 27.3 would be in there. 27.3 microwaves can't be sold. Okay, we can't sell 27.3 microwaves. So if you want to have a little bit, just a little bit more accurate representation based on the actual word problem itself, then you might want to simply say, okay, we're going to use whole numbers for our beginning and end boundaries of our interval. So if we want a whole number, okay, let's look at 27. When we sell 27 microwaves, do we make a profit? Well, no, 27 is to the left of that intercept. So actually that's a loss. So 27 is not going to be in this interval, okay? 27 does not lie between 27.097 and 228.187 or 197. So the next greatest amount we could put in there would be 28, okay? 28 microwaves give us a profit. So because it actually gives us a profit, I'm going to put a bracket on it because it is part of your solution set. And then what whole number would be the boundary at the high end of your interval here? Well, would it be 229? No, 229 is not between these two zeros. So we have to look at 228. Okay, so the number of microwaves sold that will generate a profit overall has got to be between the 28th microwave, including the microwave number 28, and 228 microwaves. So from 28 to 228 and including those two values, those are the numbers that will give us a profit. Okay, that is the end of 2A. Hopefully you enjoyed day 3. Hopefully you will enjoy your optimization project, and look forward to seeing all these projects in class. Okay, I think it'll be fun. All right, see ya.